Everyone to the seminar. So today's speaker is Jessica Turner. Jessica did her master's degree in Glasgow and then went on for a PhD at Durham University at the Institute for Particle Physics Phenomenology under the supervision of Silvia Pascoli. So she worked in neutrino physics, first on kind of labor symmetries and then also kind of leptogenesis. And then she moved on for a postdoc at Fermilab and broadened her perspective in the work she's working on. And since last year, she's a faculty member at Durham University at the IPPP. And today she will be telling us about towards an all orders calculation of the electroweak bubble wall velocity. So please, Jessica.
Okay, thank you very much for the very comprehensive introduction and the invitation to speak with you all today. I'm really pleased to do that. I'm going to shrink the video box down, so if you have questions, just shout out at me during the talk. So I will perhaps apologize in advance. This has got quite a lot of details, but the devil's in the details, and hopefully the calculation is clear. And as I said, just stop me if you have any questions. So how we're going to begin today is talk about what exactly is a first order electroweak phase transition and what are the motivations for having one. Given that this is an all orders calculation of the electroweak bubble wall velocity, we're going to start with the leading order interaction, which is a one-to-one interaction, and we'll go over that in quite a bit of detail. Then we build on that intuition to study the work done by Bodecker and Moore on the 1-to-2 interaction in the relativistic bubble wall case. And then I'll discuss our work where we look at an all orders calculation of the velocity, and then I'll summarize. Okay, so as you all know, within the standard model, the electroweak phase transition is a crossover. However, it's quite easy to make the electroweak phase transition first ordered with minimal new physics, even at tree level. Why might one want to do this? Well, there's a lot of rich physics associated with having a first order electroweak phase transition. These include generation of the matter-antimatter asymmetry via electroweak baryogenesis, the creation of topological defects such as cosmic strings or primordial magnetic fields, and interestingly, also the creation of a stochastic gravitational wave background. So there's a lot of interesting cosmic relics we can possibly observe from this first order electroweak phase transition. So what do we mean by a phase transition? I'll be very, very brief with this because probably everybody knows it. But we have this Higgs, let's say a Higgs effective potential as a function of the field space for 3 different temperatures. At temperatures above the critical temperature, there's only a single minima. However, as the universe expands and cools, the potential may develop a second minima, which is degenerate with the minima at the origin. This occurs at the critical temperature, and below that temperature, we can have a first order phase transition if there's some sort of thermal bump separating the false and the true vacuum. And in order for the field to move from the false to the true vacuum, there's tunneling, and this is a binary process in a sense. It's not a continuous process, and when this binary process occurs, you get nucleation and percolation of bubbles of the broken Higgs phase in the early universe, or whatever phase of scalar you're looking at. Naturally, inside the bubble, you have the broken phase where the Higgs field sits in the true minimum, and this is a lower energy state, and outside the plasma remains in the false vacuum until the bubbles expand and all of the universe is filled with the false vacuum. So this is just another picture of what's going on. As I said, we're going to calculate today the relativistic bubble wall velocity of if we had a first order electroweak phase transition. So how does the velocity actually come about? So we saw that we can get these first order phase transitions occurring with minimal new physics, and these bubbles nucleate in the early universe and they expand. The reason they expand is because we have vacuum pressure, which results from the symmetry breaking Higgs potential. And this is model dependent. That depends on the structure of the effective potential in your new physics. However, just as you have pressure driving the bubbles to expand, You also have frictional pressure of the particles which interact with the Higgs bubble and can enter it or be reflected. And this contributes towards a thermal pressure, which can retard the expansion of these bubbles and slow the bubble wall down to some terminal velocity. And this is relatively model independent. And it's the balancing of these two pressures, so the vacuum pressure from the symmetry breaking Higgs potential and the frictional pressure from the interactions of the early universe standard model plasma with this Higgs condensate, that results in a balance of forces from which we can find the terminal velocity of these bubble walls. So the terminal velocity of the bubble walls is impactful for a number of reasons in terms of these early universe cosmic relics that could be generated from these first order electroweak phase transitions. And the first one I'll briefly discuss is electroweak baryogenesis. So in electroweak baryogenesis, we have these strong first order electroweak phase transitions that can satisfy Sakharov's conditions. Essentially, particles in the early universe thermal plasma in the symmetric phase can reflect off or be transmitted through the bubble wall. At the bubble wall, there are CP violating interactions, and it's through these reflections that you can generate a chiral charge asymmetry. Inside the bubble where the Higgs has a non-zero VEV, the electroweak Phaleron processes are suppressed, whilst outside these electroweak Phaleron processes are not suppressed. That's important because essentially the chiral charge asymmetry you generate from this reflection off of the CP violating bubble wall gets reprocessed by these electroweak Phalerons into a baryon asymmetry. Naturally, this is happening in the context where the bubble is expanding. So the bubble expands and the baryon asymmetry gets zipped inside the bubble where the Phalerons are suppressed, and the baryon asymmetry can freeze out for all time. So this was proposed in the sort of early to mid 80s, and it's been extremely well studied, this mechanism, because there are very close connections with Higgs physics which can be probed at the LHC and via various neutron DMs and electron EDMs, those sorts of things. And the electroweak bubble wall velocity affects the efficiency of this transmission and reflection, which in turn affects how efficient electroweak baryogenesis is. A second observable which is affected by the velocity of the bubble walls are the gravitational waves which are generated by the bubbles. So the bubbles themselves can perturb the background metric in a number of ways, and that generates a source of stochastic gravitational waves. So the way the bubbles generate these gravitational waves is through their collisions with each other, through the generation of sound waves which can form in front of the bubble shells, and also from the magnetohydrodynamical turbulence generated as the bubbles percolate in the early universe. And these contributions, so the collisions of the walls, the sound wave contribution, and the turbulence contribution have different gravitational wave spectrum. And essentially, depending on how fast those bubble walls are moving, these different contributions can have different weights. So if the bubbles tend to move more fast, then the collisional terms, the collisional contribution tends to have a greater contribution towards the gravitational wave spectrum, and the spectrum tends to have a higher amplitude. Whilst if the bubbles move more slowly, it's actually the turbulence which has a larger contribution and it has a somewhat more suppressed amplitude. So just to summarize, the motivation for first order electroweak phase transitions is the generation of a number of interesting cosmic relics we want to explain. Secondly, the bubble wall velocity affects not only the efficiency of electroweak baryogenesis, it also affects the stochastic gravitational wave background, which may be measured in the coming years by Lisa. So that's why it's of interest to calculate this, this property of the bubbles. Okay, so before we begin, there's a lot of kinematics in the rest of the talk, so I want to define what I mean by various kinematics and state some assumptions. So we have these bubble walls that nucleate in the early universe. We're going to approximate them as planar because we're kind of studying them at the point where they've become sufficiently large. The bubble walls, we can approximate them as planar. Secondly, they're expanding in the z direction, just generically, that's how we take it. And because they expand in the z direction, the bubble walls inherently break z translation invariance. And what that means from Noether's theorem, we know that longitudinal momentum or momentum in the z direction must not be conserved when particles interact with the bubble wall, right? So I have a particle A, it is coming from the symmetric phase because here the bubble's moving to the left. It's interacting with the bubble interface, which we will assume is just a step function. So it's infinitely thin barrier that separates the symmetric phase here from the broken phase here. Anyway, this particle can interact with the wall, and its longitudinal momentum can change across the wall if it changes masses, if it changes its mass. So how do we define this kinematics? So here we have PAZS. So this is the Z momentum of particle A in the symmetric phase. And we define this via the following dispersion relation. So it's simply its energy squared minus its transverse momentum squared minus its mass squared in the symmetric phase. So S here will be standing for symmetric phase, and H will be standing for broken phase. Those might be mixed up between soft and hard, but if they're ever on a kinematic observable, it means symmetric and broken phase. Likewise, the broken phase longitudinal momentum is the same expression, but we substitute the symmetric phase mass with the broken phase mass. So energy and transverse momentum are conserved because there's nothing in this system that breaks them. Therefore, we know that the transverse momentum of the particle entering the bubble will be the same as the transverse momentum of the particle inside the bubble. Likewise, there's nothing breaking time translation invariance, so energy is conserved in these interactions. Okay, so we're going to begin with the one-to-one calculation, and this was studied by Peter Arnold and Bodekern Moore back in 2009. So, as I said, the friction results from the scattering of particles that couple to the Higgs condensate, or in particular the bubble wall. A quantity of interest for us is the Lorentz factor of the wall, gamma. So we're just going to study what is the impartation of particle A onto the wall. What momentum does it transfer to the wall? So the transfer of momentum from particle A to the wall is just the difference of the longitudinal momentum of particle A and particle B. And that from the previous slide's kinematic is simply this expression here. However, in the remainder of the talk, we're going to study the limit where the walls are moving relativistically, so they're accelerating relativistically before they reach a terminal velocity. So for us, EA and EB are very, very large relative to all other mass scales, so MAS and the transverse momentum PBH. So we can tailor expand these expressions, and what we find is that the transfer of momentum to the wall is just the change in the mass squared across the wall of this particle divided by twice its energy. And that's simply delta m squared over 2 gamma t. So very heuristically, the pressure is just the force over the area, which is just the change in momentum over the area times the time, which is just the flux times the change in momentum. So we just did this quick calculation to find the change in momentum. Then we just need to determine the flux. So in the rest frame of the wall, so the wall's stationary, the particles are coming in extremely fast with a large boost in the z direction. So normally the flux would go like t cubed, but because the particles are coming in very fast in the z direction, there's a Lorentz contraction in the z direction, so the flux is gamma t cubed. So putting the flux together with a change in momentum, we find that the gamma factor or the Lorentz factor of the wall gets cancelled, and the resultant pressure from this one-to-one interaction is simply gamma naught t squared delta m squared over 2. So I know gamma to the naught is 1. I'm just doing a little bit of power counting. Okay, so we can formalize this heuristic argument into a more let's say master equation. So the pressure for one-to-one is simply the sum over all of the incoming particle species flux multiplied by the differential probability that particle A splits to particle B times by delta PZ. And I'm going to refer to delta PZ as an observable. And that's simply the transfer of momentum from the particles to the wall. And then we have some quantum statistical factors which account for the fact, is the particle coming in a fermion or a boson? So this differential probability is simply the phase space of the final state particle multiplied by 3 Dirac delta functions. 2 account for transverse momentum conservation, 1 accounts for energy conservation. In a normal homogeneous background, we'd have a 4th delta function accounting for the fact Z translation would be conserved in a homogeneous background, but it's not. So we don't have that delta function. Instead, we have our observable. And then we have a delta function here that just says the case we're interested in is the case where the particle does not change flavor across the wall. So it simply gains its mass. It's just the same particle traversing the wall and getting a mass, thereby imparting pressure, momentum onto the wall. So putting this expression together, we get the following form of our master equation, and we can always decompose the phase space of particle B into the transverse momentum and energy and longitudinal momentum, just using the on-shell condition of particle B. And we integrate over the phase space of particle B, massage the terms a little bit, and again, we find that the pressure for the one-to-one goes like T squared delta M squared.
Jessica, can I ask a question for clarification? So this kinematics and then the calculation assumes that the wall is rigid. There is no recoil of the wall.
Yes, this assumes the wall's rigid and infinitely thin.
Okay. So what would be if it's not rigid? It fluctuates. Well,
I would think the observable or the transfer in momentum would be more complicated because you'd have to take into account that deformation. And also if it was
what is the reason why I can ignore these fluctuations? Are there any obvious reasons why I consider the wall rigid?
Short answer is that not considering the wall rigid is actually very, very tricky in terms of these calculations. The long answer is, I think in this regime where the walls are moving relativistically, probably how much you would distort the wall is not particularly large in a length scale compared with like 1 over the energy of the incoming particle.
Okay, yeah, thanks.
Thanks for the question. Anyway, this is the basis of our leading order interaction, so that's pretty important to understand this. So as I said, Bodecker and Moore looked at that 1-to-1 back in 2009, and the implication of this gamma to the naught was quite profound because the vacuum pressure driving the expansion doesn't scale with the Lorentz factor. It's just a function of the structure of your effective Higgs potential. Since the friction doesn't scale with gamma naught, that meant the bubbles can accelerate to close to the speed of light and run away. Therefore, your gravitational wave signal would be very, very big. So that was the implication of this calculation. However, very interestingly, in 2007, the same authors revisited the calculation and proposed that the 1-to-2 interaction, which we're going to spend a lot of time on, actually is significantly more important than the 1-to-1 interaction. So here's the basic picture. As Akil asked, the wall is infinitely thin and it's rigid in spite of its interactions. This is in the Bodecker and Moore paper. Here the wall's moving to the left. We have particle A coming in. It's on its mass shell. Through its interaction with the wall, it's put off of its mass shell. It produces a soft particle, PC, which is a gauge boson, and then there is a hard particle with momentum PB. So I should just say this 1-to-2 interaction could never happen in vacuum because you need some sort of interaction to put PA off of its mass shell in order to create what would be a massive particle PC and PB. And the idea Bodecker and Moore had here is that you can convert the incident particle's energy into the mass of a second particle and some non-trivial transverse momentum of the final states. Naturally, these transverse momentums have to balance because there's no braking in the transverse direction. And the idea is that the transfer of momentum from particle A onto the wall is can be significantly larger than the 1-to-1 interaction precisely because you've used some of the energy to create two particles in the final state and redistribute the transverse momentum. Okay, so we can go back to our master equation we had on the first slide, where we have our flux of incoming particles, our phase space, some quantum statistical factors which account for the nature of the incoming and outgoing particles. Again, we have our observable, which is a momentum transfer, and then we have our 3 delta functions, and we have some matrix element squared, which tells us how probable the particular interaction is. So here we can just rewrite this expression in the following way. We've integrated over the phase space of particle B, and we've just kind of massaged the phase space of the soft emission particle C. So this factor in the yellow box here is a combination of the observable plus some phase space factors that came from integrating over phase space B and rewriting phase space of C. So Bodecker and Moore are particularly interested in the following kinematic regime. First of all, the incoming particle is hard. That's given in the fact that the bubble walls are relativistic, and in the rest frame of the wall, the particles are coming in hard and fast. Note that they're on their mass shell. The transverse momentum of the incoming particle would be of most order T. And for it to be on its mass shell, we know that given that the energy is of order gamma T, the longitudinal momentum will be of order gamma T as well. In this regime, the masses are small relative to the energy of the particle. The mass of particle A would be its thermal mass. In terms of the outgoing particle, we have a hard particle, particle B. Its longitudinal momentum is close to its energy in this regime, and its mass again is small compared with the energy. And finally, we have the soft emission given by particle C, where at most the transverse momentum can be of order T or MC, and the longitudinal momentum will be small because this is the soft emission. And we'll see why they go into this particular kinematic regime shortly when we study the matrix element squared. So anyway, we have our expression for the 1 to 2, and we have this term we want to massage a little bit in the yellow box. So here on the denominator, we have PBZS and PCZS, which are respectively the longitudinal momentum of particle B in the symmetric phase and particle C in the symmetric phase. So we can rewrite the longitudinal momentum of particle C in the following way. We've just taken the dispersion relation from that fourth slide I showed, taken out the energy, and we're going to do a Taylor expansion. This parameter here, epsilon, encapsulates how collinear that soft emission is, i.e. how big PC is. If PC is very small, then the emission's highly collinear with PB, the hard particle. Then we can rewrite PBZ, the longitudinal momentum of B, in terms of the following dispersion relation. And that is approximately EA1 minus X, where X is the softness parameter, which is just EC over EA. This is often used in collider physics and splitting functions. Right, so we'll take that term, and having rewritten our longitudinal momentums in the following way, we can rewrite this as simply 1 over the energy of A times the energy of C, and the numerator is given by what we'll call the transverse mass of particle C, and this is really X times epsilon. So those two small parameters that told us about the softness of the emission and the collinearity of the emission. So now the pressure looks a bit more simple. So we just have the phase space of particle A, which will give us the flux once we integrate over it. We have the phase space of particle C, some quantum statistical factors, and this very, very simple factor after we did some massaging, and we still have our matrix element squared to calculate. So how do Bodecker and Moore calculate their matrix element? Well, they calculate in the following way. They consider particle A transitioning to particle B and C, and they have some interaction Hamiltonian. And the matrix element is given by an integral over the Z direction of mode functions for particle A, B, and C times a vertex function. So so I did explain the mode functions. I just wanted to see, sometimes if I don't have enough time, I might skip what these are, but I'll explain where they come from. So these mode functions are treated using the WKB approximation, and essentially they're an amplitude. And in Bodecker and Moore's case, they approximate this amplitude to be 1, which means that all incoming particles penetrate the wall, and then some non-trivial phase, which is an integral of the longitudinal momentum over z. So this very much looks like wave functions for one-dimensional quantum mechanics, where you have a potential, and you can have wave functions propagating to the left and to the right, and that's essentially what this is. And these mode functions essentially encapsulate the fact that the bubble creates an inhomogeneous background for the particles. So just a very quick summary about where these come from. Let's consider a scalar interacting with the bubble wall. This is the Lagrangian here. You see that the mass term is homogeneous and changes, is inhomogeneous, I should say, and changes as a function of z. Of course, the field equation, or the Klein-Gordon field equation associated to the scalar is simply given by this. And if this were a homogeneous mass parameter, then the solution to the field equation would just be a phase as a function of the energy of the particle and the 3 momentum weighted by some complex number. However, as I said, the bubble creates an inhomogeneous background and an inhomogeneous mass term. So one makes an ansatz for the solution to this field equation, where you have a phase of energy and a phase that's a phase associated with the transverse momentum, but not a phase associated with the z momentum, because that's not conserved. One would then take this ansatz, plug it back into the field equation, and what you find is that the solution to that field equation is just the mode functions that I showed you before, where we have an amplitude and a phase. And as I said, this is analogous to one-dimensional scattering of particles off of a potential well. And in Bodecker and Moore's case, they take these mode functions to all be positive in terms of the phase, and all of the amplitudes are 1. And that suffices to say that all of the particles are transmitted because the bubble is moving so relativistically that essentially the particles all have enough energy to penetrate the potential created by the bubble, and there's no reflection as a consequence of that. So the matrix element is given here, and now that we can see where these mode functions come in, we can plug in the mode functions and integrate from z equals -infinity in front of the bubble up to z equals 0, which is where they define the bubble wall to be, and then from the bubble wall all the way to the back of the bubble wall at z equals infinity. And this is just simply this expression here. And the arguments are simply the arguments of the mode functions, AS and AH. So this AS corresponds to like the mode function in the symmetric phase, which when you actually plug in the kinematics, it's the change in Z momentum between the incoming particle A, the final state B and C, and then AH, which is analogously the change in longitudinal momentum in the broken phase, as denoted by H here. So one performs this integration, and then what you will find is the matrix element looks like this. So there's some normalization factor to IEA. Then you have the difference of the vertex function in the broken phase, denoted by VH, over AH minus the analogous term in the symmetric phase. So to summarize, these AHs and ASs in the matrix element tell you about the fact the bubble breaks Z translation invariance. Whereas VH and VS, as we're going to see, come from the nature of the interaction itself. One thing to note is that when we square this matrix element, these 1/A terms very much resemble propagators, but they're not fully covariant propagators. They're propagators only propagating in the Z direction. Okay, so we're almost there. So we square our matrix element, and what Bodecker and Moore find is they can pull out this vertex term, which is something I'll return to because it's not obvious one can do that. And you have a functional difference of these mode functions. So the vertex functions are related to the splitting functions, and they have the following form. For example, we can concentrate on a hard fermion splitting to a soft transverse gauge boson fermion, and it pretty much looks like coupling squared, transverse momentum of the emission, the soft emission VT, over x squared, which would denote its energy or its softness. As you can see, for these vertex functions, if x is small, then the matrix element becomes large, And that essentially corresponds to the intuition that you're much more likely to emit low energy radiation, and therefore the matrix element becomes enhanced. Okay, so this is a very quick recap on the splitting functions, but I don't think I need to go over that. Let me just check the time. I need to move a bit faster. Okay, so we have our AS's and AH's, and they're just the difference in longitudinal momentum in the broken and symmetric phase, or symmetric and broken phase respectively. If you plug in kinematics, what you find in the relativistic regime is you can approximate AS and AH as just the transverse mass of the soft emission in the symmetric phase over X, and the same term, but in the broken phase over X. So then we can essentially plug in these expressions for AS and AH, and what we find is that the second part of the vertex function has the following form. So it's a difference of the mass squareds of the emission, C, over their transverse mass squared, and there's 1 over X squared, essentially coming from this denominator term. And then what we want to do is we want to look at the structure of the whole matrix element. So now we've calculated what the mode functions look like. We can plug in the form of the vertex function that would correspond to the emission of a transverse boson, which just goes like essentially K transpose, which I will use as a proxy for PC, the soft emission, over X squared. As you can see, these X squareds cancel. This X squared came from the mode function. This one comes from the vertex function. And this is the final form of the matrix element squared. And I just emphasize this cancellation because if you, for example, had fermion going to a, let's see, a fermion, let's say a scalar going to a scalar transverse boson, you wouldn't get this one on X squared, and therefore your matrix element would be proportional to X squared, which is very small. And that's why for Bodecker and Moore, this particular interaction of the emission of a transverse gauge boson is significant because the matrix element isn't suppressed. But in our master equation, we had the matrix element squared times our quantum statistical factors multiplied by our observable, which is our change in momentum integrated over the flux. So we have our change in momentum here, and if we multiply all this out together, we find the following form of the matrix element squared times the change in momentum. So it's proportional to the essentially the mass of the broken phase emission, because I'm going to ignore the symmetric phase mass of the emission, given that it's very small in the case of a W or a Z, and we have 1 over X here. So there's just 2 things left. We need to multiply by the flux, and we need to integrate over the transverse momentum and energy of particle C. If you take the prior expressions and you do that, what you find is that you get the following expression. Well, first of all, Bodecker and Moore cut off their, they assume that the phase transition supercooled, or that the thermal masses are much, much smaller than the bare masses, and they cut off both of their integrations by the mass of the emission. So if you do that and put everything together, what you'll find is the 1 to 2 pressure goes like gamma T cubed, which is the Lorentz contractive flux. 1 over m squared comes from the transverse momentum integration. 1 on m comes from the energy integration, and this m to the 4th came from the mode functions. So if you cancel off the m's, you'll find the pressure goes like m gamma T cubed. So just to summarize, the pressure for them goes like gamma. It does not scale like gamma to the naught. And since the vacuum pressure doesn't grow in gamma, a terminal velocity will be reached. Moreover, their pressure is directly proportional to the mass squared. So if there's no phase change, the pressure goes to 0, and that's relatively easy to see. Their matrix element is a function of WKB and a vertex function, and that vertex function is dominated in the soft regime. They cut off both their transverse momentum and energy integrations by the gauge boson emission mass. And I thought this was a very interesting paper at the time, and my collaborators and I at least felt we could kind of use the physics of scattering or collider experiments to model the momentum transfer from the incoming particle to the wall. Because typically where you see these vertex functions is they come from Altairelli-Parisi splitting functions, which are the basis for a parton shower. And based on that intuition, you might expect that there's a large center of mass energy in between the wall and the incoming particle. So you may expect there would be many emissions, and I'm going to try and motivate that. So I'll discuss work I've had with my collaborators, Stefan Hucke, Jonathan Kosachuk, Andrew Long, and Yi-Quinn Wang. And the idea is the following. So in Boddicker and Moore, in the one-to-one interaction, we have a hard incoming particle on its mass shell. It interacts with the bubble wall and it gains a mass inside the bubble wall. So this dashed line is an interaction with the wall. 8 years later, they looked at a particle coming in, interacting with the wall. Secretly, it's actually put off of its mass shell, or else it couldn't emit two particles in the final state. But this interaction does occur. And what they found is that the 1-to-2 process, which is actually a quantum correction on the 1-to-1 process, was significantly more important in terms of the pressure. And we want to ask the question, if the 1-to-2 was so important, will the 1-to-n be even more important? And the idea here is that we have a fast incoming particle. It can probe the wall. And this probing of the wall could potentially put the particle off of its mass shell by a large virtuality that could result in a lot of soft radiation. So how do we start doing this? Let me just check the time. Okay, so there's some, I would say this calculation is inspired by the Boddicker and Moore 2017 calculation, but there's some important deviations. So first of all, we don't use the same ASs and AHs. So just to recap, their ASs are essentially the denominator of a propagator in the Z direction. If we substitute in kinematics and approximate that the incoming, well, we go to the frame where the incoming particle has no transverse momentum, i.e. it's coming head on, then this AS has the following form. If we neglect the thermal masses, i.e. MBS and MCS, then we can simplify this even further. Note that I'm going to use K transpose as the transverse momentum from now on. And in the soft limit, AS has the following form. So if I just take X to be very, very small, then this term is not significant, but the second term is, and we just have the following simple form of AS. AH, analogously, is exactly the same, but I substitute the index S with H. Our AS comes from a different place, and I'll try and motivate where that comes from. It comes from the inner product of PAS and PCS. And when you substitute the kinematics and go to the ultra-relativistic regime, and the regime where the incoming particles coming head on, and we can ignore the thermal masses, it has the following form, which is different from the Boddicker and Moore form of AS. However, in the ultra-soft regime, it has the identical form. And the same logic follows for AS. So as you can see, the two expressions are the same in the very soft limit. However, outside of that soft limit, they're not the same, and there are impactful differences. So why do we redefine the ASs? So we do so because we want to treat the ASs as covariant propagators. And the idea is the following. The wall provides some spatial discontinuity off of which the incoming particle scatters. This scattering produces a propagator, which then can decay to two final states. So what are the ASs are essentially the propagators that correspond to the diagrams that can happen in the symmetric phase or the broken phase. So let me explain this diagram a little bit first. So here we have the incoming particle on its mass shell. It can emit a massive or massless gauge boson. And in order to do that, you create some virtual particle that can be then put on its mass shell by the wall. And the wall here is denoted by the blue dashed line. So the wall puts this particle on its mass shell. The momentum of the propagator is simply the difference of PAS and PCS. And if we apply the on-shell conditions, we find that it's simply minus 2PAS dot PCS. And this is VS, since the emission occurs before the interaction with the wall. However, this is a quantum process, so you can't really say when the emission occurred. It could have occurred before interaction with the wall or after interaction with the wall. So analogously, VS is the process where the emission occurs after the interaction with the wall, and PAH corresponds to this propagator here. Okay, so we're going to given the time, I'm going to briefly explain what happens if I have a massless soft emission, which was not the case with Bodecker and Moore, because they had to have a massive emission in order to have a non-zero matrix element. I do have a phase change. So I'm saying that this hard particle, which has some thermal mass, can gain a mass as it goes into the bubble. So this could be some hard fermion emitting, let's say, a photon or a gluon. And the reason I want to do that is because there's some subtlety actually associated with these vertex functions if you're in two different phases. So I said they were related to the Alta-Parisi splitting functions, but we can really look at the structural form of Vs and Vh. So Vs is simply this process in the symmetric phase. So I have symmetric phase kinematics. Epsilon is just the polarization vector of this massless emission. So if it's a massless emission, the polarization vector does not change across the bubble wall interface. Therefore, when I do the squaring of the matrix element, I can actually properly take the square and do the polarization sum. Whereas if you had a massive emission, it's not very easy to do this polarization sum across this discontinuity. But in this case, where PA gains a mass when it becomes PB and PC's massless, the calculation simplifies a lot, and the polarization sum is self-consistent. So the polarization sum has the following form, where this, I always forget this, this letter, I'm going to call it psi, I'm going to call it psi, denotes what gauge you're in. So if psi is 1, then you're in the axial gauge, and if psi is 0, you're in Feynman gauge. So we can calculate Vs squared, Vh squared, and the cross terms. And what we find is that they have the following structure. So in Feynman gauge, you see that they're not equal to each other, and they're not of the form k transpose over x, k transpose squared over x squared. They're actually different. Using our A's, what we find is that the matrix element squared has this following form here. Now we can go to the axial gauge, do the same transformation. Okay, if we go to axial gauge, we have some auxiliary vector, which we have the freedom to choose. If you make a smart choice for that auxiliary vector, essentially Vs is 0 and Vh is non-zero, and the matrix element has the same form as in the Feynman gauge. That's not the case. That's not the case in the Bodecker and Moore. So we were motivated by gauge invariance to choose slightly different ASs and AHs. So by making this choice of AS and AH, not only do we respect gauge invariance, and the pressure would therefore be a gauge invariant quantity, but also we derive a matrix element which corresponds to a physical process we're all very familiar with, which is essentially a decelerating charge. And because the charge decelerates, it emits some sort of soft radiation field. So taking this matrix element, we can look at it in various different regimes. So we can look at it, okay, first of all, we make the choice that the auxiliary vector is the following form. And for that form, it zeroes out the VH. So the matrix element squared has a very, very, very simple form. We can look in the case where K transpose is large relative to the incoming thermal mass of particle A. And if that's the case, then we have the following form of the matrix element squared. It goes like x squared over K transpose squared. And if you're in the regime where K transpose is much larger than the mass of particle B in the bubble and the incoming symmetric phase mass, then the matrix element again has this very, very simple form. It goes like x squared over K transpose squared. So this is the large KT regime, and this would be the corresponding matrix element. In the small KT regime, actually you recover a very similar matrix element to the vertex form of Bodecker and Moore. So in summary, our matrix element squared has the following form. You see that they are 2 logs or there's a double log if you're in the small KT regime, and there's a single log if you're in the large KT regime. And these logs can be potentially very large, and they need to be resummed in order to reliably calculate what the momentum transfer is. So the way we do this, I'll maybe hurry up a bit. The way we do this is twofold. We perform an analytic resummation, and we also perform a numerical resummation or a particle shower in the bubble. I'll briefly explain the analytic resummation. So here we have a and this is inspired by, well, this is taken from standard analytic resummation applied at colliders. So to do that, we have our radiator function, which is a function of v. V is our observable, which is just the momentum transfer. So here, this is the integrated matrix element squared. I'm just integrating over the phase space of the soft particle. I have the matrix element, which corresponded to the soft diconal of a decelerating charge, but then I have, it's not an entirely inclusive quantity because I have some non-trivial theta function. And this theta function enforces that you cannot produce a larger momentum transfer at each splitting than the momentum transfer that occurred prior. So essentially this theta function enforces unitarity. So this big V, as I said, it's just the observable normalized by gamma t, or the energy. And if you put input kinematics, it has the following very simple form. It's just k transpose squared over the energy squared times x. If x is small, it's just x. So this radiator term has the following very simple form, which came from our matrix element squared. We've motivated on the prior slides. We have our theta function enforcing unitarity, essentially. And then we have two further theta functions. These theta functions constrain the phase space, and essentially they make sure that the particles that are emitted are always in the broken phase. So we're not, we're assuming essentially the incoming particles have sufficient energy that the final state emissions will always be in the broken phase, that there's no reflection. So what's clever about this method is that you want to integrate over the phase space of particle C. So that involves integrating over the energy and the transverse momentum of particle C. Because we've taken our observable and rewritten it in terms of the transverse momentum, essentially we can do a substitution for the integration over the transverse momentum in terms of the observable. So essentially you do a Jacobian transformation on this integration, and you're integrating over the observable itself. And that's how the resummation is performed. So here, this integration over x from 0 to 1 is just a proxy for integrating over the energy of the emission, accounting for unitarity and phase space constraints. And then we have an integration over v, which corresponds to the integration over the transverse momentum. If you perform this integration, you'll find that you get something proportional to the coupling of whatever interaction was occurring times by a log, where the log's 1 over the observable, which is just the momentum transfer. So we want to resum all of the soft radiations, and the way that you do that is you use a Sudakov form factor, which is just the exponent of minus the radiator function. Therefore, the average momentum transfer of each particle is given by the following cumulative cross-section, as shown here. And once you perform the second integration, what you'll find is that this average transfer at fixed coupling, obviously in analytic resummation, you can't run the coupling, is proportional to some small number that's sensitive to whatever coupling that was of the splitting. And what you find is that since we've normalized delta pz to gamma t, I can take this small coupling, multiply it by gamma t, and I find that the average momentum transfer is of order gamma t. So taking the same physics and performing a particle shower, we find the same results. The left and right plots are just the same. They just show histograms of the average momentum transfer. It's just in the log scale, you can see some interesting features a bit better. So what we've done here is we've varied gamma from 10 up to 10 to the 16. As you can see, the momentum transfer is relatively similar across this. We've also varied the cutoff scale, and we found that as long as the cutoff scale's about 10 to the minus 3 smaller than gamma, it's not, the average pressure transfer is not sensitive to that cutoff scale. So that cutoff scale could be, for example, the mass of one of your hard legs, or the thermal mass. So what we find is that for small gamma, the particles coming in are not super energetic, and we get some interesting features in this histogram, and they actually correspond to the production of on-shell final states. You have Higgs, W, and Z in top quark. That's what these little spikes in the histogram are. And from the numerical simulation, which simulates all of the standard model degrees of freedom, we find that the average momentum transfers of order %, and therefore, since the flux goes like gamma t cubed, and since the average transfer goes like gamma t, we find the pressure scales like gamma squared t to the 4th. And we find that there's very good agreement between the analytics and numerics. So there are many points of discussion and lots of things to look into in the future. One obvious question is, where does the phase change enter? does this happen if there's not any mass change? And the answer is no. That's not in our final, that's not like in the analytic formula of the final solution, but the point is the leading order interaction would be 0 if there's no mass change. And since we've calculated an all orders quantum correction, there would be no quantum correction if the leading order interaction was 0. So let me motivate this a little bit further and tell you where exactly this hard or leading order interaction comes in. So we define some sort of hard function we've normalized our matrix element to. And for simplicity's sake, let's consider a scalar interacting with the bubble wall shown by phi here, and it changes mass. So this would be the leading order interaction. So a particle can interact with the wall, have large virtuality, and begin to shower. So what we did is we performed a Vev insertion. Essentially, we calculate this 0 order A to B matrix element, which is just shown here. S is whatever scalar we're interested in, and phi is the wall. As I said, we assumed the wall was a step function. So if you Fourier transform a step function, and we obviously have to square that, we have the following form that goes into this matrix element, this leading order matrix element. If you perform this integration over kz, what you'll find is that essentially the delta terms don't contribute because they enforce momentum conservation. The principal value terms don't contribute by definition when they're multiplied together, but the principal value times delta function will give us a 1 over delta pz. So that takes care of this phi squared, but we still have our s. So our s is just the usual scalar quantized in the normal way, and that corresponds to some phase of 4 momentum times x. If we put this together, what we find is the probability for A to transition to B is simply given by this. If we just do this integration, a bit tedious, but not difficult. And what we find is that there's a lambda phi naught squared, and that comes from the fact that S gains a mass as it enters the bubble. In the relativistic regime, the delta m pz, which we worked out in the 1-to-1 case, it was just delta m squared over the energy. Essentially, this mass squared term cancels with this mass squared term. And the probability for this 1-to-1 interaction and there is independent of the mass as long as there's a mass gained. So essentially, that's where the phase cancels here. And what that's saying is that as long as the particle is sufficiently relativistic and acquires a mass, it will interact with the bubble wall given this assumed step function form with a probability of 1. And that's essentially what we've assumed. And then we've taken, we've essentially taken Bodecker and Moore's recipe, I would say, used a gauge invariant form of that and performed the all orders calculation. So in summary, we treat this 1-to-1 process as a leading order process. So as long as the ingoing particle gains a mass, it will interact with a probability of 1, following from a Vev insertion method, assuming an infinitely thin wall. This provides our leading order process that normalizes our next to leading order process. And this isn't an ad hoc procedure. This is kind of supported by how we know how to do scattering experiments and how gauge theories factorize. And how we've essentially tested that over many years with using LHC data. So I believe I'm probably out of time, and I'll very briefly summarize and say that the bubble wall velocity is a consequence of a force balancing exercise, and we've reformulated the relativistic calculation in a gauge invariant way, and we've calculated the average pressure to all order. We find a correspondence with a charged particle decelerating and emitting a soft radiation pattern. We find that the pressure scales like gamma squared, and in fact massless soft emissions can contribute. As long as the hard leg gains a mass and there's an efficient redistribution of transverse momentum, then essentially many standard model degrees of freedom, such as photons and gluons, mostly gluons since the strong coupling strong, will contribute. And we find a good agreement between our numerical and our analytical resummation. I don't know, that must have been a spelling correction, resumption. suffice to say, there's actually disagreement in the literature, and there are lots of avenues we want to further explore. In terms of importance, probably understanding where gauge invariance was broken in the Bodecker and Moore calculation would be on the top of the list. Second on our list would be looking at finite widths of walls, because this might provide some sort of ultraviolet cutoff, i.e. it's another scale in the problem. And then maybe looking at non-perturbative effects and the contribution those can have. So thank you very much for your time, and I hope you enjoyed the talk.
Yeah, thank you very much, Jessica. We certainly enjoyed it. We have time for questions. Who would like to go first? Maybe I can start us off. So you mentioned, okay, so you had that assumption always that it's a thin wall, basically. So what do you expect? How would it change with a thick wall? And you said there is that cutoff. What do you expect, that gamma squared dependence will change, or what's your naive expectation?
I may think there might be, I'm not sure if the gamma squared dependence would change, but you may get some mass scale associated with the width of the wall. And the basic intuition is the following. So we've made, I should say, the Bodecker and Moore paper makes that exact same assumption where the wall's infinitely thin. So as a lot of our calculations based on that, we've kind of followed those assumptions. And in this paper, I mean, if we take the intuition of a particle scattering off of a nucleus, let's say, which is kind of the physics off of which this is based, right? You know, we can have an electron probing a nucleus, it can be put off its mass shell and shower and produce lots of soft radiation. By assuming what the proxy for the wall would be in that analogy is the form factor of that nucleus. And by softening the wall, essentially the hard function or this leading order function, we may not get this cancellation, which means it's mass independent. So there may be some mass dependence on the ingoing particle, essentially.
Okay, so that it depends on the
it'll also be a function of the wall width. Yeah, so that probably will feed into that. Yeah, I mean, perhaps by going to the infinitely thin wall width, the momentum transfer of that initial hard interaction is as kind of energetic as it can be. So if we introduce some finite wall width, it kind of softens that a bit.
So you basically have less momentum transfer, and you would and that would slow down the wall less. Then is that right?
Yes, exactly. Yeah.
So, interesting. Thanks. So and now with the gamma square dependence, right? You slow it down much more compared to the Bodecker.
Yeah, that's the I probably should have said that. Like, that's the crux. Yeah. Since the pressure, the vacuum pressure doesn't scale in gamma, if the pressure scales like gamma squared, the terminal velocity will be smaller than if it was m gamma.
Yeah, thanks. Any other questions?
Yeah, I realize it's quite a heavy kind of technical talk at the end of the day.
No, Michael had a question, I think.
Just a really small question. Yeah, thanks for the talk. It's really interesting. I just want to, the particle that was radiating, being radiated off, it wasn't completely clear to me if that obtained a mass as it passed through the wall or not. I guess not. And so, yeah, could you clarify that? And then like say a little bit about what would happen in the other case?
Yeah, so this particle, so there has to be some sort of phase change, or else the bubble cannot see the interaction. So this interaction, if particle A had the same mass as particle B, and if these were the same mass and particle C was massless, then essentially Vs and Vh would be the same. And
so I understood that PA and P, there's a mass change between A and B. But what about C as that comes off? Does that
So in this case, we've gone to the simplifying case where this is massless.
So yeah, kind of I guess the question is what would happen if that also interacted with the wall and obtained a large mass as it transitioned across the wall?
So we've accounted for that in the regime that the energy of this, or the transverse momentum of this particle, is still large relative to its mass. If that were not the case and you did this completely, it would be quite a big pain, because you would have to calculate the polarization sum in the symmetric phase and the broken phase, and then do the cross term. And in order to do the cross term self-consistently, you'd have to match the polarization sums across the wall. So this has been, if you want to do that precisely, this has actually been done in a paper from the 1970s. So there is a way of doing it. It's just not something we've done yet. So at least using this example where PC is massless is simple, and in the kinematic regime we are interested in, gives a qualitatively similar solution.
Yeah, sure. Okay, great. Thanks for clarifying. I understand.
Hi, can I ask a question?
Mhm.
Hi, thanks for the talk. So kind of following to what Archel asked before. So if you do want to relax the rigidity assumption on the wall, I'm just wondering, how would you actually go about modeling the material characteristic of the wall? Because I guess I don't really understand how does the wall behavior is determined. So how would you know like how elastic it would be under collision, or these other kind of or these other characteristics that it would have in order to properly model the collision?
I'll be entirely honest and say I'm not sure.
Maybe I can give you some well, partial answer. I don't have a, So the point is that this wall is the Higgs profile, right? So it has certainly the excitations, which are Higgs particles. But those particular excitations, which I want Jessica explain, which breaks spontaneously this translational invariance, would be excitations which are confined on the wall. They are basically a Goldstone bosons of the breaking by the Higgs, and so you can model those modes, which are basically fluctuation, through the collective coordinates along the wall. This is one of the way of doing this. Another way of doing this, in principle, looking at the whole wall as the coherent state of the Higgs particles and modeling that way the quantum effects in principle. But I know how, in practice that might be very complicated.
Oh, that's very informative for me. Yeah, it's something I've thought about but not investigated. I mean, this calculation has lots of assumptions and approximations we want to move beyond.
Yeah, I mean, if you take the bubble wall without Higgs, there's a real scalar field, for example. It's a very simple way to see that the excitation there are normalizable zero modes on which are propagate along the wall, and those are basically Goldstone bosons, which describes essentially the fluctuations of the wall. So in the relativity, you can't have an absolutely rigid body.
Yeah, I would agree. I mean, is the scale of those excitations, because we're in the relativistic regime, I wonder if the scale of those excitations is small relative to the kind of particles entering the wall.
Well, the mass of this excitation, they first of all, they are confined in this, the plane, but they are massless particles. They should be massless. They are Goldstone bosons, and they are normalizable zero mode. So in principle, you can play through those collective coordinates and even have some Feynman rules for those and so on.
Interesting.
So could you potentially, I don't know, run a lattice simulation to brute force this, to just see what happens along the boundaries?
Well, I don't know anything about lattice calculations.
I'll admit, unfortunately, I don't know anything about lattice calculations either. It's a very interesting question. I mean, I had someone ask if one could kind of by proxy simulate this in an experiment, like in liquid helium or something, but I've not been asked the lattice question. Yeah, I'm not sure. I mean, I'm not sure why we'd have to go to the lattice to do that. Is it because there's zero modes, or what would be your I'm just wondering, like, what's the motivation to go to lattice for that?
Yeah, I'm not sure. I don't really, haven't tried it myself either. It sounds kind of similar to when you have the like axion domain wall simulations, and they run those on like a grid, and it seems to be kind of, you have like inside of the like one phase and another phase in different patches. So I thought it might be possible to approach it the same way. But yeah, I'm not really sure if there's any real advantages or if it's possible.
This is one wall, right? There is no many walls and patches.
Yeah.
The simple win is, yeah.
Any last question?
Yeah, I might be completely barking up the wrong tree. I mean, I was also thinking about lattice simulations, but I mean, I guess for the axion case, we're really not interested in necessarily radiation on the wall or the impact on the momentum transfer between other particles and the walls. We're sort of more interested in the kind of global scaling properties of the wall network. But I mean, I was thinking, is there some kind of link between these kinds of calculations, and if we were interested in the interactions between particles and, say, like a domain wall, you know, made of the axion field, or made of you know, any kind of field, or potentially like a cosmic string, if you wanted to do like a one-dimensional, like a, you know, I guess it's a different geometry. I don't know. Is there any link between these two worlds?
I mean, I'd speculate and say there might be. I'm not sure if it would give. It's not clear to me it would give us much more insight, because at the moment, like the Higgs bubble just kind of, we're not really looking at its excitation so much as how it provides some spatial inhomogeneity.
I was more thinking sort of the other way around. Like, is there the stuff you're doing, could that be helpful for maybe understand? I don't know. Have you heard of anybody applying the kind of techniques that you've been doing to other types of object? So things like cosmic strings, for example.
I have not, but I'm not a great expert on cosmic strings. So
Jessica, the formalism which you described is a very generic. I mean, you can call this electroweak phase transition, but you can call that any phase transition in principle, right? And it might be not a Higgs, but with the axions, of course, if you have this bias symmetry where the axion domain wall decays, this is precisely the situation what Jessica describes with those walls. And I think, Kieran, you can describe it. The only thing is that the axion couples very weakly with everything else. So
yeah, so you may end up with
yeah,
with no effects
you might,
of interest. Yeah. Okay.
Yeah. Great. So yeah, thank you very much, Jessica, for a very nice